In this lesson, I'll show you how to find the angle between two planes. The question reads, find the angle between the planes x plus y plus z is equal to 1 and x minus 2y plus 3z is equal to 1. And once we do that, find the symmetric equations for the line of intersection L of these two planes. Let's start with A. To find the angle between these two planes, you can use two different methods. You can either find the magnitude of the cross product of the normal vectors, which are those that shoot perpendicular to the plane, they're not shown, and then use this formula to find theta, or you can find the dot product of those two normal vectors and use this formula. Of course, you'd solve for theta in both. For simplicity's sake, I think using this formula makes things easier. So how do we find the normal vector given these equations? It's actually not that bad. All you have to do is look at the coefficients of x, y, and z for each. For example, if you want the normal vector here, I'm going to call it A. That will have the x, y, and z components of 1, 1, and 1. I'll call the normal of this plane vector B, and that has the x, y, and z components of 1, minus 2, and 3. So both of these vectors are at 90 degrees to their plane. Next, we decided to use this formula, and that tells us that we have to find the dot product of A and B, and that can be done by multiplying the corresponding components. So 1 times 1, that's 1, plus 1 times negative 2, that's negative 2, plus 1 times 3, that's 3. This will equal to positive 2. So that's the left side of the equation. Now, this part tells us that we have to find the magnitude of A and B. Finding the magnitude can be done by squaring each of these components, adding them up, and then square rooting. So 1 to the power of 2 plus 1 to the power of 2 plus 1 to the power of 2 is the square root of 3. That's the magnitude of A. The magnitude of B, I'll write this out, 1 to the power of 2 plus negative 2 to the power of 2 plus 3 to the power of 2, all square rooted. That's the square root of 14. So we found the magnitude of A and B. 2 is equal to the square root of 3 times the square root of 14 cosine theta. That's what we're looking for. I'll use my calculator. 2 divided by the square root of 3 times 14, and then cosine inverse, we end up with 72 degrees. So the angle between this plane and that plane is 72 degrees. In part B, they ask find the symmetric equations for the line of intersection. To find the symmetric equations, and we've done this in one of our previous videos, you actually need to have the equation that represents this line right here, what I'm hovering over. To find the equation of that, you need a point along this line, and you need the direction vector. Let's start by finding a point along this line. To do that, we can set the z-coordinate of both of these equations equal to 0. And if I set z in both of these equations equal to 0, I'll end up with two equations that have only x and y. And then from there, I can actually solve for x and y as a system of equations. In case that's confusing to you, here's what I mean. So setting this equal to 0, I end up with x plus y is equal to 1. And setting this equal to 0, I have x minus 2y is equal to 1. Here we have a system of equations that you can solve for x and y. Without showing you the steps, you should end up with an x value of 1 and a y value of 0. Putting it all together, we should have a point along this line that is at 1, 0, and 0. I also mentioned that you need the direction vector. Now, because the line lies in both planes, it is perpendicular to both the normal vectors that we extracted earlier from the equations. Therefore, the vector that I'm going to represent as v is technically parallel to L, and it can be found by taking the cross product of the normals. Let me show you. So I'm going to call this vector v, the direction vector for the line, and that is equal to the cross product of A and B. Remember, A was 1, 1, and 1, and to find the cross product of two vectors, the trick is you write it out twice, so 1, 1, and 1, write it out again, 1, 1, and 1. The other vector B was defined as 1, negative 2, and 3. 1, negative 2, and 3, 1, negative 2, and 3. Just remember this pattern. 1 times 3 minus 1 times negative 2. So 3 plus 2, that's 5. That's the x component of the direction vector. Again, 1 times 1 is 1 minus 1 times 3, that's negative 2. 1 times negative 2, that's negative 2, minus 1, negative 3. Now we found the direction vector, and we can write out the equation of the line, and it too is a vector, as the point that we found written in vector form, so 1, 0, and 0, plus a scalar quantity times the direction vector. The next step after this would be to write these as parametric equations, and from there we can use the parametric equations to come up with these symmetric equations. Although you can just jump right into that. So A, B, and C represents 5, negative 2, and negative 3. So 5, negative 2, and negative 3 as the denominators. X minus 1, y minus 0, and z minus 0. That's z. And there you have it. That is how to find the angle between two planes and their line of symmetry.